Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous series, we completed our discussion on the structural optimization of autotransformers. Now we begin a new, equally important topic: impulse overvoltages. These high-frequency oscillations can be even more dangerous than regular operating voltages, especially during lightning strikes or switching surges. In this video, we will examine how such impulses are distributed across the winding, why the first turns are the most vulnerable, and how this voltage is calculated. What is an impulse overvoltage? It is a short-duration voltage spike in an electrical system caused by lightning discharge, network switching, or transient processes during a fault. It is characterized by a steep front rising within 1 to 5 microseconds, amplitude exceeding the rated voltage by 3 to 5 times, and short duration, typically 10 to 100 microseconds. Why impulse voltages are dangerous? They add on top of the operating voltage and greatly intensify the electric field. They damage turn-to-turn insulation between layers, and the tank or shielding structures. The most vulnerable parts are the first turns from the grounded terminal and line exits of the windings with non-standardized insulation. Initial voltage distribution. When an impulse with a steep front reaches the winding, the voltage is distributed unevenly. The winding behaves as a system of capacitances, between turns, between layers, and between turns and the tank. Formulas shown on screen, from 7.1 to 7.7, describe the capacitance between two adjacent turns, equivalent diameter, and calculation for cylindrical layers. The steeper the front, the less time current has to spread. As a result, the impulse voltage accumulates on the first 3 to 5 turns. Geometric factors. Voltage distribution depends on the shape of turns, whether round or rectangular, the density of winding, the insulation material, and the spacing between turns. Example: with an impulse of 250 kilovolts applied to a winding of 100 turns, the first 5 turns may receive up to 40% of the total impulse. That means each of these turns may experience 15 to 20 kilovolts instead of 2 to 3 kilovolts that would be expected in uniform distribution. Practical use of the model. The capacitive divider model is applied during insulation design for impulse voltage testing and in transformer simulation using computer-aided design tools. Simplifications are acceptable if the turns are identical, the structure is symmetric, and parasitic couplings can be neglected. Practical analogy. Imagine you suddenly push water into a long garden hose. At the very beginning, the pressure is much higher than in the middle. If the hose is old and weak, it will break near the inlet. The same happens in a transformer winding. The impulse hits the first turns the hardest. Practical task. Calculate the capacitance between 2 turns with the following data. Diameter equals 25 millimeters, radius equals 3 millimeters, and length equals 0.5 meters. The calculation formula is shown on screen. Determine the voltage falling on the first 5 turns when the impulse is 200 kilovolts with a front of 1.2 microseconds. Today we have learned what impulse overvoltage is and why it is dangerous, how an impulse is distributed across the winding, which parameters affect this distribution, and why the first turns suffer the most. In the next video, we will dive into the wave nature of impulses and explain how harmonic analysis and front theory are used to describe the propagation of voltage through a transformer winding. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.